Okay, so from the lab yesterday, what did the rays do for this type of lens? The optical toy box. What happens with this guy? Phones away, please. Bam. This one goes together. Okay, so did something like this. Oops, that's horrible. Okay, pretend those are straight. All right, this is known as the focal point. So if you had, this is where you would start fires with a magnifying glass. Good with that? Okay, rays from the sun coming in are parallel. This is known as the focal length. Okay, and this is a converging lens. Okay, here's how this works. You see how this arrangement of the prisms is similar to converging lens. Here it's thin on the ends and thick in the middle. Okay, so when this ray of light goes in, it bends towards the normal line, and then when it goes out, it bends away from the normal line. Good. Does the same thing on this one. Causes it to bend in. Okay. This is happening at a not so abrupt case, but shaped like this causes light to refract to a single point. Good? Okay, focal point. All right, so if we have to figure out what image is going to be formed, I'm going to give you two different ways to do that. First way is with a ray diagram. So, if you're drawing this on your notes, a very important dimension here is this focal length needs to be identical to this focal length. It doesn't really matter what that length is, it just needs to be consistent from either side. And draw your object far away from the focal points. Okay. This is known as the principal axis. It's just a reference line to help us draw stuff. Good? Okay. Don't draw this. Just listen on this part. The fact that we can see this object means the light's being reflected off of this object in all different directions. Okay? I'm just going to focus on one point, is at the very top. Okay? Don't draw this. Light's coming off of this object in all different directions. I only care about 3 of those specific rays. Okay? So, everybody good with that? Picking 3 of them. Now you can start taking notes or drawing what I draw. Okay, the first one, we're going to start at the top, always start at the top of the object, and we're going to go parallel to the principal axis. Having a straight edge would be beneficial. Okay? So the first one, it is parallel to the principal axis. Then refracts through, through far focal point. parallel, and then it's going to go. Does that make sense? Based upon, oops, what we talked about here. Okay. That's the first ray. The second ray is we're going to employ this idea here. If I reverse this ray and I went through this focal point, how would the light bend after going through this lens? I think it's like going to go back down this way. It's going to refract parallel. This idea, like if I can see you in a mirror, someone else can, like they can see me type thing. If I'm reversing this light, it's going to go in that same direction. Okay, so we're going to use that same idea to capture for this second ray. So the second one is we're going to go through the near focal point, then refracts parallel to the principal axis. Okay, so we're going to go through the near focal point, and when you get there, it refracts parallel to the principal axis. How are we doing with that idea? Okay. The third ray, in my opinion, that's my favorite. It's the easiest. Goes straight through center of the lens. Take a straight edge, go straight through. Hope is they intersect all the same spot. Okay, so the reason why this we can go straight through is because on top of the line, this would bend it down a little bit. Below this principal axis, it bends it up. These are considered thin lenses, so the fact that this is thin, it's a pretty good approximation to say, you know, it just goes straight on through. There's not really much bending that takes place. Good with that? Okay. Now, where those rays intersected, this is the top of the image because we drew it from the top of the object. Okay. What does that mean? The bottom is still connected to the principal axis. It's the top. It's below it. So that means our image is going to be upside down. So we talked about the characteristics of an image a little bit when we did the mirrors. Okay, so upside down, we're going to say is inverted. Okay, and it is shrunken or enlarged. It's smaller than our object, so it's shrunken, and it is real. What? So this is the light rays actually cross or intersect. Okay, not ready to actually cross or intersect. So as I walk around, grab a lens.
It's like the opposite of like a mirror, that like an opposite of like a convex mirror. No, it's just like a magnifying glass.
So it's similar to a concave mirror.
Yeah. That's what I was thinking earlier. Like I thought it would be like a convex like mirror, but
So we'll get to this is similar to more of a concave mirror. Okay, make sure you have a positive, like there should be a sticker on there. Make sure that's a positive number. Positive 100, 150, 200, 250, it needs to be positive. Okay, here is what you're going to do. You're going to take a piece of paper. You are going to sit down. You're sitting here like this. I want you to swing your legs out facing this way. I'm going to take your piece of paper and put it out like this. Take your magnifying glass, your lens, put it between the sheet of paper and the screen on the board, and move it until you can see an image of the board. It's hard for you guys to see, apologize, but that worked. Okay, so get it focused. If it's not focusing, move the lens nearer or closer to the piece of paper. You should see an image of me. Put it on the screen. Put it on the piece of paper. Put it on the piece of paper. Oh. So the image, you could describe that as, is it upright or inverted? And inverted, is it shrunken or enlarged? Shrunken. The fact that you can project this onto a screen means that it is real. Okay, and we'll talk about what is the opposite of real momentarily. Okay, if you need help. So you're looking at the piece of paper, not through the lens. This right there. You're gonna look on that side. There you go. See that? You're looking at the piece of paper. You're not looking through the lens. You're looking at the piece of paper.
If you are there,
yeah.
You can like, if you like and you like unfocus your eyes, it goes
upside down. Okay, we're good? Okay, that's real. The fact that you can project that, put that on a piece of paper, on a screen, says it is real. Okay? Now, kid taking tests, that would be, yeah. He's a senior. All right. Okay. Here's a popular misconception. Did the image form at the focal point? Did the image form at the focal point? No, it did not. Did not form at the focal point. The only time you can get an image at the focal point is if you take the image of the sun when you're trying to burn stuff. Okay, it was super far away, crazy far away. Okay, all right, all right. So now we're still going to use a converging lens, but we're going to move the object in front of the focal point. Okay, so again, if you're drawing this on your notes, make sure that the focal lengths are equal. And then you put your object, I'd put your object closer to the focal point rather than closer to the lens. Oh, no, just kidding. Put it like somewhere halfway in the middle there. Okay? So, you draw the first array. Draw the first array. Draw the first array. There it is. Focus.
I'm trying to focus.
All right. Hopefully you said this. Parallel principal axis through the far focal point. Good? That was ray number 1. Ray number 2 is through the near focal point. But when we do that, it's like dude, you missed the lens entirely. Does everybody see that our problem there? So what we're gonna do to make this, to do this thing, we're going to put our straight edge connecting from the near focal point to the top. Okay. And we're drawing this as if there was a ray of light that connected those. Then which way is that going to go? That's going to go parallel to the principal axis. Okay. And the third one, my favorite, the easiest, straight through the center.
So if I held it like this, oh, whoa, you're upside down and focus.
Oh yeah, we didn't do that. Okay. In order to do the previous one, take your lens at arm's length, wink, and look at something far away. It is inverted. It is inverted, shrunken, and you can't perceive if it's real or not. But the fact that you can project it on the screen is real. Good? Okay. So now, coming back here to this example, what do we notice happens to the rays? Do they intersect? Uh-oh. That's not good. Oh, man. Okay. If rays don't intersect, then extend refracted rays backwards. If the rays don't intersect, then extend the refracted rays backwards. All right. So, which one is the refracted ray, A or B? B is the refracted ray. So we're going to extend this. Use a straight edge. And we're going to extend that backwards. Good with that? Which one is the refracted ray? For blue, A or B? B is the refracted ray. So we're going to extend that backwards. Okay. And the green one, no, it's not bent, so we're just extending this backwards. The hope is they intersect all the same spot. So here is the top of the image. So our image, you could describe it as upright, enlarged, and virtual. Okay. So that's the opposite of real, meaning that you cannot project that onto a screen. But why can you see it? So, sorry, let me hit this. So if you have to extend the rays backwards, that means it is a real image. Okay. Sorry, if you have to extend the rays backwards, that means it's a virtual image, not a real image. Okay. Your eyes are a converging lens. Like the lens in your eye is converging. And so even though it doesn't make a real, this doesn't make a real image, your eyeball brings it together and makes an image on the back of your retina. Okay. We can see virtual images because of this. You just can't project it onto a screen. But this is where we use magnifying glasses to read things. Close. That makes sense. So you can like use this as a magnifying glass. Bring it close. Make things enlarged. Good? Okay. Questions there? All right. Next up is a diverging lens. Okay. Here, what we see is everybody good with how diverging lens and this are like similar? Thick on the ends. So this diverges as if it came from a point Oof. Divergent lens. Good with that? Okay. To form a ray diagram of a divergent lens, we're going to the roles of the near and far focal points are switched. The roles of the near and far focal point are switched. What does that mean? Well, in this first ray, we're going to go parallel to the principal axis. If it was converging, we would go through the far focal point. But we're going to make that through the near focal point. Does that mean it bounces back? That would be reflection, not refraction. But this comes as if it came out of this guy through the near focal point. See how that corresponds with what we just did here from the near focal point. So maybe like from near focal point. Okay. So the next ray would be reversing this. If we shot a ray of light towards the far focal point, it's going to refract parallel. Okay. So we're going to look at through the far focal point. So we're lining up a ruler, straight edge. As if it was going to go through the near focal point and then it refracts parallel. Good with that? Last one. Easy peasy. Goes through the center. The light rays cross. Nope. So what do we need to do? Extend it backwards. So the red one's easy. It just follows that dashed line. Extended that one backwards. The blue does not do that. We need to extend this one backwards. The green one, well, the green one is there already. And so we find this is your image for a diverging lens. So your image, upright, and you tell me, you figure it out. What are those in? What's the three characteristics of that image? Okay, I'm going to be passing around a diverging lens. Okay. So just look at stuff and then pass it back. Pass those around. Okay, look at something. You can look at something close or far away, doesn't matter. Pass that around. There you go. I got you. Okay. How would you describe the image? Yep, does not matter how far away you are, it is always the same. It is always shrunken, upright, and virtual. So it's upright, shrunken, and virtual. Good? There you go. Oof. Shrunken, upright, and virtual.
Just make it normal. You can zoom in with it. No, you can zoom in with it. You can zoom.
Okay? Good?
Oh, yeah, that's a kill.
All right. So that's one way. The other way is with math. Okay? Now,
Mr. Smiley, is that how like scopes on a rifle work?
yep.
They have like two of these, one's inverted,
There's probably more than just two.
oh my gosh, I'm super
Okay. This is how a camera works. This is how anything with a lens works. These are lenses.
Mr. Smiley, if you look into this, can you see my eye?
If I had good vision, yes.
I'm super zoomed in on your
Okay. Now, here, okay, look at the stickers on your lenses. Does everybody see, like, everybody should have a positive one. That's a convergent lens. If you have a divergent lens, that's going to be a negative focal length. Okay? There's a sign convention with these lenses. Okay? This is this is lens maker equation. 1 over the focal length is equal to 1 over the image distance plus 1 over the object distance. Okay? It has a similar flavor to resistance in parallel. Remember the 1 over R plus 1 over R equals 1 over R, that thing? Okay? So same kind of trick, same calculator button, the inverse button. Okay? And then magnification. This is equal to negative di over do. It's also equal to your height image over your object height. Okay, the height of your object, height of your image. Good with that? So those are the equations you're going to be dealing with. Okay, I will give you this sign convention. You will not need to memorize that. Okay. All right, so quick example. So let's say you have a divergent lens, has a focal length of 50 centimeters. What is the image distance of an object that is 80 centimeters away from the lens? Okay, so if you here's the important thing. If you're given a number, you must assign a positive or negative value to that based off of this sign convention. If you're given the number, you must assign a positive or negative sign to that. If you're solving for something, just leave it alone. Don't assign anything, and the answer will come out in the math. Okay? You're given a number. So here I'm given a focal length of 50 centimeters, diverging lens. I look at this, oh, that's negative. Okay? So this is going to be negative 0.5 meters for the focal length. here, the object distance in this class are always going to be positive. Okay, so I've got a 1 over, I'm using Lensmaker's equation. I've got a negative 0.5 meters is equal to 1 over your image distance plus 1 over 0.8. And I'm solving for di. I feel like that is a 3 point something. So we have 0.5 inverse minus 8 inverse equals 3.25. Recognize that is not the answer. You need to find the reciprocal of that, just like with resistances. Hit that button again, and you find that to be a negative 0.31. Okay, so that's 31 centimeters. The fact that it is negative means that, oh, it's a virtual image. What did we get when we did a diverging lens? We got a virtual image. So it's like, oh yeah, that works great. Okay. If we were trying to find the magnification, we just do a negative, because that's part of the equation, negative 0.31 over object distance 0.8. Magnification is a positive 0.3, so 0.34. 0.38. So what that means is it's upright, and the fact that this is less than 1 means it's shrunken. Like if you have a magnification of 2, that means it's enlarged by twice. Height is 2 times. Does that make sense? Okay. So your worksheet that's due tomorrow doesn't touch this. We'll pick that up soon, but the refraction worksheet due tomorrow. Okay. All right. I need those lenses back.